Hey everybody, welcome to the stream. It is another Sunday. We're going to finish up chapter 7 of Essentials of Compilation today. Um, and then we're going to talk about what to do next. And I mentioned some of those things that I want to do next, or potential things I want to do next on the previous episode. But we'll go into some of those today, and I would love your suggestions in the chat. If you jump in the chat and drop them, that would be great. Also, want to know what you think of um, sound. So today I decided to turn on a noise suppression filter on OBS and see if that helps with the sound quality. If it makes it too clipped or just sounds weird, let me know. I would love to know how that is going. So where we were last time, we had done a lot of generate prelude and conclusion. And I think that we had it mostly feature complete. So we're gonna wrap that up today. Depending on time, on like the level of our progress, we might go back and do a refactor that I've been talking about for multiple episodes, which is that we early on in this chapter we decided not to call a block start inside definitions. Um, and I think that what we want to do is go back and change that. Um, I think the reason why, first I was concerned about collisions, but in those intermediate forms, it doesn't matter because they're still scoped inside a definition. And so, if you see a jump instruction to start or a go to start, it's still scoped within that definition. And it's not until that very last pass, the generate prelude and conclusion, that we get rid of the definition concept. And we talked through that last time. Um, and the nice part about the prelude and conclusion is that if we have it, do an unconditional jump to the start for the function that we're generating prelude and conclusion for, then what we get is the bits that are about setting up the stack, pushing registers that need to be saved, aligning the stack. All those bits are in one block, and it's um, at this level. I don't know that we need to be so concerned about efficiency. Like a jump instruction is, not a big deal. Um, and the assembler and the linker will do things to the code anyway. So there's, it could be that unconditional jump gets inlined. But it would be nice to be able to see that as a separate piece in the output assembly code. So we may get to that. Anyway, let's switch over to our code screen and see what we're up to. So this was one of the tests we had open. Last time we were doing all of this, and I think that, so there's just some formatting things going on here. I think that what we were trying to enable, is this. So we want our UI to be able to do the entire program. Remember, if you want to follow along, here's the repo. You can, go follow it there. Here, our CI pipeline failed because I didn't format the file for whatever reason. Okay, so that did not work. All right. So I need to do Gleam run, Luster dev start. And then it'll all be built and we can refresh here. Okay, so let's take our typical program. I think this is why I had this open, is so that I could just, copy paste it. And let's compile the entire thing. Okay, so it might be illustrative to get to like some phases that are, we can step through this. Tokenize, we don't care about what tokens output are. Parse, we've got, and this is just reformatted. Interesting, there's a lot of returns there. Okay. Type check, we have type wrappers around vectors and such. Yeah, and then, it looks like we're wrapping functions as well. Okay, and then shrink does some transformations. So it injects the main function. Yeah. And uniqueify renames variables, so we can see that each of those variables gets a suffix on it. Reveal functions just attaches the arity there, so we know in this case, map has arity 2, inc has arity 1, and so forth. Limit functions. I don't remember what that phase does. So let's look at reveal functions. Okay, so we have removed some of the wrappers, has type wrappers in that phase, which is fine. Oh, right. Limit functions is also about um, making sure that we keep it to 6 arguments. So if there's a trailing argument, or if there's like 7 or 8 arguments, that last argument becomes a vector. And that lets us, have functions of many, many arguments. Okay, expose allocation is going to do all of the GC things that are required for vectors. You note that this gets sufficiently more complicated. And that's because we're doing this, virtual operation global value to look at the heap pointers and so forth, and call into the collector. Do explicit allocations, um, and there's this if, call the garbage collector. Okay, and then uncover get is about wrapping mutable variables. So we wrap the mutable variables with an explicit get, and this makes sure that it's treated as a complex operation rather than just um, anyway. It's a marker for a later pass, and that's just to enforce that variables that get written to multiple times get updated. Are treated in a way that their side effects are apparent in the later passes. Okay, and then remove remove complex operands. Make sure that, so let's go back to uncover get, and you might see a little bit of a change there. Note that these functions are just bare right here, but you have to treat function references as complex operands, so they get assigned to a variable. This, when we write the assembly code later, this turns into load the address of this function into a variable and eventually a register probably. Okay, and that lets us do the indirect call. Okay, and then explicate control is the big pass that turns all of this, which is just like expanded functional code with some side effecty calls, into an imperative code. So this is the ordering is implicit in the structure. And here we're turning it into, it's a sequence of statements, basically. So, you see a lot of the same things, but we're assigning things to variables. So this is sometimes called three address code. And yeah, and so kind of looks a little bit like C, or just, you could think of it as just something imperative. All right, and then go to select instructions. This turns the C-like into assembly-like. We have assembly language with variables. I think, walking through this transformation is like, it's really instructive in terms of how the concepts map from layer to layer. Even though, we have covered all of this before in my stream, if this is your first time to the stream, you may not have seen this. And we have these little things in our pretty printing of the AST that, like, we get the live before sets and so forth. So now we're going to prepare for register allocation by doing liveness analysis. And you can see here we have, the heap pointer R15 and the stack pointer RSP. And then some, these other blocks, we have some variables in addition to registers. And then, we have like argument registers in the live before set and so forth for functions that we call. Okay, and then we do, there's another one, which is a pass in the middle between these next two, which we don't show, and that's just building a data structure, which is the conflict graph. So like, for example, like temp1 cannot be RSP or R15, like that sort of building of conflicts. And that gives information to the graph coloring algorithm, which is in allocate registers. So here we're going to make sure at the end of this pass, all of the variables are replaced with registers or stack locations. So we'll see, things like temp1, vecinit1 disappear. Okay, so now we've got basically we haven't used any stack locations, but we get RBX, R12, and so forth assigned these. These variables. And then there's the patch instructions pass, which is going to do some minor like peephole optimizations. I say peephole, that's probably not the right word, but they're like, hey, look at this instruction, and is it actually necessary, or do we need to inject some instructions here where the semantics of a particular instruction requires a few things. So I think we still have a bug here. That is surely not right. Anyway, okay, so patch instructions, one of the things it does is remove redundant moves. So like move RCX to RCX, we don't need that. So that will get eliminated. And there are cases where potentially we have like a stack or heap location, which is in an argument that can only accept a register. So we may see those changed to be replaced with move that thing to REX and then use REX in that next instruction. Okay, we'll see. All right, so let's do patch instructions. So you can see that move RCX to RCX was removed. I don't think we've injected any REX bits in here. I still think this 88 is very suspicious. We may have a bug there. And then finally, generate prelude and conclusion is going to, you notice places here like jump main conclusion. There's no block in here, main conclusion. Or jump map conclusion, jump inc conclusion. Those do not exist. So we'll generate them. We will also, for each of these ones where it's the name of the function, we'll be injecting the prelude into there. And I mentioned when we started, I might want to remove that and say like this bit, which we've been calling the name of the thing, should be start, and then the prelude will be injected into the name of the function. Okay, so here, things get reordered It's not a big deal. Um, but here our inc we got, so previously RDI was the argument, um, and now we have so that's the first argument to this function, but now we've got the stack alignment and so forth. So restoring, like setting the base pointer for allocations that might be spilled to the stack, aligning the stack pointer, and then we go into our normal extract the function arguments. Okay, but if we scroll down, we should find inc conclusion down here somewhere. Yep. So it does the reverse. It realigns the stack pointer and then pops the value that was there into RBP before returning. And then map is going to push some of the call esave registers that it had allocated, and then it does the stack alignment bits, and then it's zeroing out the heap slots that it's going to use. So this is like just making sure that the offset of R15 here, it's dereferring R15, the 0th offset, and putting 0 in there in the 8th, 8 byte. Is that right? Yeah, 8 byte offset, putting 0 there. Okay, so and yeah, so then we have some, this indirect call queue bit is turned into a deref on that register RBX. We have where are arguments? So we're moving RDI, which is argument 1, into RBX. So that's a function pointer. RBX now contains a function pointer. And so let's find main, where it calls let's see. So here's main. It's saving all the registers, aligning the stack, and this is about the calling initialize. So this is, hey, give me a heap of 64K, I guess. And then so it calls this initialize thing, which is in the runtime. And then so initialize will set this global root stack begin symbol, and so we're putting it into the heap pointer or the root stack pointer, and then we're initialize. We know we need a vector, a single vector, so we're zeroing that out. So initializing it to 0. And then we're bumping it by 8 bytes. So this is just saying, we have this slot, which is going to be a vector that we are allocating to. And now, so just for reference for later on, we've got the map function in RBX, and we've got the inc function in R12. Okay, and then we are initializing our vector. So these are the initial values into our vector. We're copying the pointer to the heap, to the free pointer on the heap into RCX. Sorry, I keep saying this is the heap. This is the root stack pointer, right? And then we're basically, bumping it. So we're allocating 24. That's for the tag, the first value and the second value in there. And then, we're doing the do we have enough space check. Yeah, so it's like, say, hey, if it's less than, then, we have not reached it. Otherwise, we jump to block 3, which is calling collect. Okay. So if we jump to block 2, that does nothing. So assuming we have, sorry, no, main block 2 probably, yeah. This again is just does nothing. Okay. So if we're in main block 1, we're putting the pointer to this newly allocated thing in R11. And then we're bumping that pointer so that it points at free space that we have not allocated yet. Okay, and then we're putting 4, which is the vector tag of this is a vector of size 2, 2 integers, and we're putting that into the first slot in R11. And here, I think that, again, I think that this is wrong. This 88, that can't be right. We got some redundant moves going on here. I'm not sure why. Okay, so now we have put so this is loading the initial values. R13 goes into offset 8 of R11. And then RDX, what did we use RDX for? I don't think we used it for anything. Anyway, yeah, I think we've generated some bugs here. Anyway, R14 was 41, so we're moving that into the slot for R11. Yeah, I think this is just a null. This is like a void operation. This RDX doesn't do anything. Okay. So here we're loading the arguments. So R12, remember, was the inc function. We're putting that into argument 1. And then RCX is, the pointer to our vector. So we are putting that into RSI, and then we call map. And then we copy it out into our vector space, I'm guessing, and we're moving that into R11, and then we are getting the value from offset 16, so element 2, and putting in RAX, and we jump to the conclusion. So, this makes sense here. We are doing, we're creating this vector, we're calling map inc on it, and then we're extracting index 1, which is the second one. So obviously the answer to the program is 42. I think, so in the conclusion, looking at this, we are resetting the root stack down a slot. So this is saying, we're no longer using that. Realigning the stack, popping RBX and all the registers that we saved, and then return. Okay, so I think that, other than this suspicious 88 offset, which I think that there's an 11 something times 8 somewhere, and I think that we changed that last time, but I don't know that what we changed was correct. And I think that this is in select instructions, and it's probably down here, not compute tag. Is there a root stack? No. Or is it in allocate registers? Yeah. So Right, so if it's a vector, the location it gets is a root stack assignment. Right, so here we must be getting a is 0. Um, which, why would we get that? I think that's assuming this. So I think we remove the subtract 11 because why would that be assigned 0? Let's see where else, like where we would assign that. Okay, so this is just picking one. I think so. Right, pick color with a saturation. It, I think the pick color doesn't take into account, I mean, obviously doesn't, whether the item is a vector type. And neither does this color graph step. The main problem I see with this, if it needs to treat these differently, then okay, let's look up here. Okay, for each function definition. Okay, so we do the complex and we color the graph. And then we extract the assignments. So assuming this is like the vector gets assigned RCX, then that actually becomes this. And because it's 0 minus 11 times -8. So I think that we actually need to that assumes that they would be allocated to the stack. They'd be spilled to the stack. But if we're not using enough registers to force spilling to the stack, then then it's really just this. Now, this is going to break tests, of course. Um, let's get to select instructions. Okay. Okay, and R11 is our generic, like, this contains a vector register for allocations. Okay, so we go to allocate registers. Now it's like 0 offset R15. That makes a lot more sense. Because R15 is the root stack, right? But here we're getting negative 88. Why? So main before... Maybe it's that we're using this for two different things. So if I put that back, the question is, does the internal part of map still have negative 88? No, now we have the opposite problem. So here it's, yeah. But up here we have positive 88. So, oh, um, let's see if we can figure out why that is. Why does map so this is moving the arguments, right? Let's look at select instructions. Okay, so v2 is getting assigned 0 on the root stack, but why? I think it's just arbitrary. Like up here, it's saying, oh, you know, you need to be assigned to the stack. All right, let's look at select instructions. So I'm going to keep flipping between these because I want to understand this behavior. Okay, so this line RCX from, yeah, or any of these. Okay, so R11 is receiving the heat pointer, right? Okay. Um, and then we want to put that into the root stack pointer. Okay, so this alloc3 becomes the 88. Yeah, I think something about this algorithm, it just assumes that the vectors will always spill to the stack. And thus you can say, but like the coloring algorithm does not consider the type. It just picks a random vertex that doesn't have an assignment. Okay, that's this pick color. And pick color does not consider, again, does not consider the type. What I want to do, just to be sure that like I didn't miss something, is let's look up root stack, which is going to force us to go back to chapter 6. And what we want to look at is what they talk about for register allocation here. So, okay. Okay. Garbage collector needs to access all the pointers in the root set. That is all variables that are tuples. So the root stack is used for spilling tuple type variables. And if a tuple type variable is live during a call to the collector, must be spilled to ensure that it is visible to the collector. Okay, fine. The latter responsibility can be handled during construction of the interference graph by adding interference edges between the call live tuple type variables and the callee save registers. Okay, so this is essential. I think that we've gone over this before, but like we need to make sure that this is correct. And it's saying they already interfere with the caller save registers. Because you have to call alloc and collect. Right? Okay. So we will look at the build interference step and make sure that that's correct. And I think that we did this before. So, right. So if it's a vector, we add a conflict between this location, like variable, right? And all the callee save registers. Um, right. Type information for variables. Recommending. Okay. So this we were passing directly. So spilling of tuple type variables to the root stack. Hello! Welcome to the stream. The spilling of tuple type variables to the root stack can be handled after graph coloring. In choosing how to assign the colors to registers and stack locations. The program output of this pass also record the number of spills to the root stack. Okay, so we might need an additional step. which would be to rather than just have that arbitrary math in assuming, because like, okay, so the caller and the callee save registers, the union of those two sets does not cover all registers. There are still registers that are not in the calling convention, and they can be used for whatever. Um, so I think what's happening is those are getting assigned. So in some cases, our tuple type variables are getting assigned to one of those sets that is not caller or callee saved. And that means that, and that's like a low. So I mean, we can look at that, right? All right, where is it? X86 global. Wait, that's not right. X86 base, that's what we want. Okay, so these are all the registers that we have to work with. There's 15 of them, right? If we go down and look here, so there are 7 callee save registers, and there are 8 caller save registers. I wonder if we're just not getting a conflict injected. It's probably right. Could I please ask something? Of course, ask something in the chat. I'll be happy to answer. I'll do what I can. Okay. I think it's really just that we're not creating conflicts. They say it's already interfering with the caller save registers, but clearly it's not, because it's getting assigned to RCX, which is 0 in the rank, right? RCX is 0, which would give us negative 11 for that subtraction, times negative 8 is negative 88. So I think the issue is we just need to make sure that in build interference that we create conflicts here. So we're just going to make sure, be a little bit paranoid here. Just make them in conflict with everything. So it's like vectors are in conflict with all frickin' registers. And then let's see what happens. Okay, here's our thing again. Let's go to allocate registers. Okay. We're still getting this 88, so that's incorrect. Let's look at map. It still gets 0. So that didn't solve the problem. That theory is maybe not quite debunked, but the other possibility is if there's no call, should we just go ahead and regardless of a call or a move queue, should we just put in here and I think that we had it before and it was like up higher. We looked at the types and I don't recall why we did it this way. This is 3 weeks ago, so not that long ago. I think that we need to consider ones that are not even involved in calls. Like we should always spill to the stack, except that because they're tuple typed, they get moved over to the root stack instead of the call stack, right? Okay. So I think what I want to do is we're going to do this as a pre or post processing bit. Which means that these two things get collapsed because we don't care about whether there's a call yet or not. So, which means we don't need to pass in the types. Again, I'm going up here. So, we're going to take this and we're going to we're going to just make a new function here. Add tuple type conflicts. And again, I still don't know that this is going to work. But and then we're going to pipe that to determine conflicts. Okay, so let's generate that function. Let's use this type alias because that is a mess. Okay. So we're just going to make all registers. The thing is, I don't know that. Yeah, REX is caller saved. I think this is really just it expects REX to be overwritten, so that's caller saved because that's where the return value comes from functions in this ABI. So we're to say list append the callee save registers, caller save registers. Okay, so that's basically all registers. And now we're going to dict fold over types given the graph. And this is going to require, so what is the function? Okay, so it takes the graph and then the key, which we don't care about. Well, we do care about, okay, so this is the name. So, sorry, function in the IG name and then the type. And let's do use. So use IG name type. Use is fun. Okay. So what we're going to do is do another fold, a list fold. If type is vector t, we don't care what the contents of it is, then we'll do the we'll do list fold. So this is a register that we need conflict with. All registers. Okay, so we're basically going to add a conflict. So interference graph, add conflict to this graph. And what does that take? That takes 2 locations. So what we need is location var for the name and location register for the register. And then if it's not a vector, then we just return that. Okay. All registers. So I don't know that this is going to fix the problem still. Down here, we were special casing on is this a call or not? And then, you know, execute rule 2, which is what we should do in that case, but also sorry, this adds registers. Okay, right. What we can do, I think, so let's go ahead and do this. What this should do then is force since, you know, R14 is 10, it should force the vector to spill to the stack, in which case our math will work out. Just pray. Okay. Danish, I'm at L3U. Did you want to ask your question? Please. Go ahead and ask your question. Okay, now we've got a bug. All right. Pattern match failed. Add tuple type complex. Why would that fail? Console. Shrink it down a little little bit. Um, oh, add conflict requires the nodes to be there. So I think what we need to do is just make sure that all registers I don't know why. Yeah, okay. Let's just make sure that we're going to make sure that all the locations are in there. And now this is I think it's worth Okay, so we've turned all of those into there, and then let's do set from list. Turn that into pipe. Oh, that did not work. Okay. Format, please. Yeah. Something's going on there. Oh, well, let's comment this out and say to do and then reformat. Okay. So now the registers are set, um, which means we can do this. Let's do set fold. And then we're going to the thing is that the register should be in there. I think it's really just that this location, this variable's not there. Yeah, let's not turn it into a set. Let's just do list. There's no reason not. But we made sure that here, turn in convert to pipe. Okay. Okay, this is just make sure these are register locations. So what we need to do here is make sure that add locations does insert location. Okay, that's idempotent. So we can just say insert location var, and then we can do add conflict between var and reg. Let's get rid, since that's a pipeline, get rid of that. Okay, so I think that this is a bit more correct. Let's see. Okay, could close that out. let's get our example, because I may have. Right. Here's an example we've been working with. Let's go to allocate registers. All right, so that's main has 0 offset of the root stack. That's good. Map has 0 offset of the root stack. So that is telling me we fixed this numerical bug by essentially enforcing that all tuple type variables are spilled to the stack, except that they're not spilled to the stack. They are right. So this needs to happen respective of liveness. It's not a choice I would make. I think it's fine to put these things in regular registers, but for the sake of the garbage collector, they need to be on the root stack. And because remember, this root stack pointer is being passed as an argument to collect. So collect needs to look at that and go, what's live in here and so forth. Okay. And let's look at patch instructions. Okay. And generate conclusion. So I think that fixes our issue with dereferencing R15. Note here that this is like decrementing the root stack pointer. I imagine map does that as well. Where's map conclusion? Right. So it's like, hey, I used 1 slot in the root stack pointer, so I'm going to bump it down. Danish Ahmed, I still have not seen your question. Please ask if you still want. Okay. So that seems like a pretty good place. Let's look at the tests here. We probably need to re-enable these. Yeah. So we are going to let's look at our patch instructions tests. See, make sure these are all enabled. Yes. Okay. And we're going to grab these functions, and we're going to replace these. And we're going to add patch instructions. All right, let's go up to the top. That's fine. We are going to uncomment all this and make sure that these things pass. We will probably go ahead and make a snapshot test as well, because we don't have anything for this latest stuff. And I think that's important to do. So this L2 needs to be Lfun. x86 global needs to be I think that's def call queue. And then we get to do these fixes again. Okay, so here we're going to do let assert x86 call queue dot this is just saying that we have one main function, and then let's rename this to main. And then we'll just rewrap it. Let's see, we're at 235. Okay. Hello, Willie. Welcome to the stream. Um, you missed it, Willie, but we fixed a big bug, and its roots had issues with the interference graph. And I say it's a big bug. It wasn't a huge bug. It was just like, where the heck is this coming from type of bug. And it was only happening because we hadn't sufficiently covered adding conflicts for all vector type. So all tuple type variables. So, okay. Okay, so the issue here, this is flat. So we're gonna call, let's rename this P2 blocks. And we're just gonna get main out of there. And this will be call queue. The other thing here is that we need to update all these. Okay. So we're gonna have to do these fixes. Right, okay, and here we've eliminated the arity on that, so um the other thing here is we're not jumping to start. So this is about generating the prelude for the main function. So let's see if there's a main conclusion. So what I want to do here is say, rather than main body, I just want to say, because we didn't do the whole start business, rather than assert equal list prefix, there's no prefix function on list, the list module. List contains, that's just an element. All right, well, let's make a little is prefix function. So this is going to be a B. Um, if A1 equals B1, then we want to say is prefix A rest, B rest. Okay, and then if we have empty A, we're going to say, and then this is true. And then anything, let's move that down. Anything else is false. Okay, so are we gonna have to do this like, let's just make fun is prefix and pull it out. Okay, so what I want to say here is, oh shoot, where was this one? Right. Okay, I want to say is prefix the main instructions for the main body. Okay. Um, yeah, I don't know that there's a better way to do that. Okay. So let's fix all these references. Call Q. Oops. Call Q. So at least this test types. I need to import that. Import that. If A is a prefix of B. Okay. All right. And this particular one, I think what we do is let's fix this. So this is a list of definitions. Oh shoot, that was wrong. So what does a definition take? Why is that being so weird? Here. Okay. Now we can fill the labels. Okay, label is main, return L.integer t, and then blocks is going to be this dict from list. And I think that what I want to do here is new definition and just override the things I care about. Okay, and this is going to be Okay, so we want stack vars is 3. We don't care right now about types and conflicts. Or used collie or root stack size. So let's just move. Okay, now I can move it because it just needs to go up. And get rid of that. Okay, format for me. Thank you. Okay, so this needs to be not start, but main. Um, and then this needs to be, all these need to be call queue. And this is just going to be a list of blocks. Not a list of blocks, just a dictionary of blocks. And then we're going to take what is here in start and put it in main because we didn't do this refactor. We're going to get rid of start. And that stack vars thing goes away. Okay, and now I need to change all these to x86 call queue. Thank you for bearing with me, folks. I know that this is not the best, but here we are. We're going to make it work. So we're nearly there. All right. And I have a feeling this test might fail because things changed, right? Um, the other thing here is that main needs to be global. So I think that what I need to do is this. And then conclusion, let's just fix all these. What happened there? Okay. I have a feeling this is going to fail, but we will see what we get. And then we'll make a okay, Gleam test. Okay, so we are going to have some bugaboos here with that fix that we made. So I kind of want to do maybe that separately. From fixing the test. Okay, so What's fixed? That's fixed. Those are correct now. Don't care about that. But the main thing is the derefs for the root stack pointer are correct. I'm not certain about this. Which test is this? So allocate registers multiple functions test. Yeah, okay. So this particular test, right? So root stack size and stack vars. What I'm wondering is, did we mess up the computation of the root stack size or the stack vars? Let's look at that. So map gets a root stack size of 1. Yeah. And main doesn't change. I'm wondering why map previously had a root stack size of 2. That's interesting. Hello, Kythera. Welcome to the stream. Um, so there's a question in my mind about whether, like, I think that we don't. Its root stack size is 1 because that's what it allocates, right? Um, it allocates a new vector to return. It gets a vector as an argument, but that argument doesn't need to be. It's interesting that this is the second argument gets put into that slot. Right, and we're allocating the output vector. So we should see that we get R15 offset 8 somewhere down in here. We're getting 0. So what I'm wondering is, well, this is just the allocate registers. We haven't looked at the prelude and conclusion, because what should actually happen is that we bump the R15 pointer, right? And that way, right. And so this is moving the allocation into the root stack pointer down here. And this is just, it gets a different register because previously we were using RCX for something. That's fine. Yeah, I think that this is accurate, that it only has 1. And I'm wondering, go ahead and accept that diff. And let's look at the next one. Okay, so this is patch instruction tests. Okay, here we've got the 88 business going on. Went to 0 as we would expect. You've got, yeah, stuff going in. We're using a different register. That's fine. Mm-hmm. Which program is this? Yeah, this is the map inc test. So it's the multiple functions. Yeah, I think that this is fine. I'm just looking at the diff here. The main thing to notice is that 88 becomes 0, which is correct. So like this 88 should never have been 88. It should be 0, 8, 16, so forth. This 88 is a math bug where we're using the rank of our registers, or rather the rank of what would be a stack spilled location to specify the offset for the root stack, which is not correct. It's not correct if you don't also have a conflict between tuple type variables and all registers. Okay. Which is what we enforced. Yeah, it's interesting this change from RDX to RCX. We have a move that makes no sense here. Of course, this is just a void. This is a void. This is like assign void to this other thing, and it's just an artifact of our the allocator code. Okay, so the main. So this is what we jump to after we have successfully determined that we can allocate. And we're setting the tag offset 0. We're moving R13, which is the initial argument 1, into offset 8. We're moving R14, which is the other initial argument, the initialization argument of the vector, into 16. That's fine. Okay, and then okay, so we've got the function to RDI, so this is inc, by the way. We've got the vector, which is an RCX, into RSI. Interesting, this is a deref. Yeah, I guess that's correct. So it's still going to be a pointer, right? Pointer into the heap. Okay. Yeah, I think that this, so then we call and we move REX back into our slot on the root stack. So we use the result and we basically overwrite that. And then we move it back into R11, which is where we do our vector operations, and then we pull out slot 2, which is offset 16, put that in REX, and then there's the end. Okay, so that the main looks correct to me, and I think that what we're going to see down here are the same essential changes. Um, right. So after we've allocated, we put that in the root stack. We're setting up all the fields of it, which are um, where's our call queue? Or do we do that up here? Yeah, so we do the two calls, right? And those are put into, so like R12 is the first one, and then RBX is the second one. Um, and so we should see down here R12 getting put into the vector, RBX, the second one getting put into the vector, and you return it. Okay, so I feel confident this is correct. Let's look at the other failures now that those snapshots are correct. So so this multiple roots test, allocate registers test, line 236. And I think that yeah, this should be 2 because how many allocations are made? 1, 2. Although this should be there should be 3. It's immediately dereferenced, right? But we do need to allocate that, so there should be 3 on the root stack. So let's throw this. I want to see how that evolves. Let's throw this into our UI and see what we can get. Okay, so we're going to go back up here and let's look at expose allocation. And what I want to find is, let's maybe go back a bit. So right, so we're constructing a vector of A multiple times, but they're stored separately. This does not pull this out into a variable. Reveal functions doesn't do anything. Limit functions shouldn't do anything. Expose allocation is where we get all this code. Okay. So we got let A, let B. Then down in here, we have, then is A1. Okay, so then we've got alloc 10. So alloc 10 right, it has this type. And then we're setting, we've got A1 is being put inside it. And then we return alloc 10. So we should have need to immediately do vector ref 0, right? This is a dumb program, by the way. Okay, so let's compile that. Okay, remove complex operands. So what we should see, yeah, just additional lets. Explicate control, let's look at this. Make sure this makes sense still. Okay, so we're allocating for vector A. So main block 8 just goes to main block 7. So we allocate a vector of integer. We set it with 42 and assign that to a.1. And then we've got vecnet 5 is a.1. That's going to go into B. So we're going to say we need to make sure that we can get, another 16 bytes. And then if we do, we go to main block 5, which branches to main block 4. Okay, so here's B. We're allocating vector 1 slot. And then we set vecnet 5 from up here. So a.1 gets put into there. Vecnet 9 is also a.1. This is for this vector allocation. And again, we're going to check. So block 2 is successful. Let me go to block 1. And here's block 1. We allocate a vector. It's a vector integer. We set alloc 10. Okay, and then temp.10 gets alloc 10, which is this. We vectorate, we get that out, so that's temp 11. So we've gotten to this expression. And then we ref out slot 0 of temp 11. So that is assigned to temp 12. And then we've got B. We're going to get vector ref on that. So that's this expression. We vector ref off of the temporary result there, right? And then we add those two together. So we got temp 12 plus temp 14. So that all looks good. Nothing suspicious there. That looks correct. Select instructions. Here's what's going to get interesting. Okay, we've not done any of the liveness analysis. This is just converting those blocks into assembly from the C-like language. They're still variables. Okay, let's uncover live. And this does the data flow. So here, we've got the root stack pointer and the stack pointer. Okay, and then main 8. Right, so vecnet 1 is the 42 that's going in there. So you see those are correct. That's going to main block 7. These actually have the same live before, which makes sense. Okay, and main block 7 also has the same ones because that shouldn't have been changed. Okay. And then we're going to 5 and 6. So 5 and 6, this is about allocating the vector for B. Right, and they end up going to 4. Okay, and then 2 and 3 are the bits for this one, this allocation. So again, it's about, do we call the collector or not? Because we're trying to allocate a tuple type variable to the stack, or to the heap rather. Okay, and then they finally go 2 and 3 go to main block 1. So here, B is live, vecnet 9, which is basically A, is live. Okay, this all looks fine. Yep. Okay. Allocate registers. So we're getting That's interesting. Negative 8. Does it grow down? I don't know. We should make sure that this makes sense, though. Um, and that it shouldn't be positive 8. Let's look at the book real quick. Allocate space on the root stack to make room for spill, incrementing the stack pointer. Right. So if you increment the pointer to make room for a new slot, then your dereferences should go down, not above it, right? So if you're adding to it, then the space that you made should be before that, right? So I think that the negative offset is correct. We should see a negative 16 in here somewhere, though. Or this computation is incorrect. Because we need this. So I think that we should see... You shouldn't reuse slots, right? Even though when you get... After you get the allocation of this, A is not really live anymore. And so this thing could take its slot. Maybe that's what it is. You've given up A's slot to this because A is no longer live. But I don't know that that's in the logic anywhere. That doesn't make any sense. I guess it would, though. If where this value gets placed doesn't have a conflict with where A is placed. That would be interesting. But that's deep in the graph coupling algorithm, right? Like A is no longer live after this thing is, except that in order to initialize this thing, you have to put A into it. So let's see where it puts the value of A2 into that. So let's go back, uncover live. Okay, so vecnet 9 gets moved into that slot. So let's watch this, hopefully, and see what vecnet 9 becomes. Sorry, we're going to have to go back one more time. vecnet 9, it's below the move of this allocation into R11. Okay. So it's in RBX. But that's just the pointer to it. That's interesting. Um, okay. Okay, so patch instructions does some bits. And let's look at prelude and conclusion. Um, yeah, I think like the essence here is this assumption incorrect? And I think 2 makes sense, right? Because since A doesn't need to occupy a root stack slot, because after it's put in this and put in this, it no longer is a root because it's not live anywhere down here after those execute. So it doesn't need to be a root. So this vector can occupy that root slot. Yeah, a little bit confusing. Um, I think you could argue for either one. Like 3 would be kind of on the paranoid side, but it really does depend on um, what the graph coloring algorithm is. And I think that if we go look at allocate registers, right? So it's computing. Yeah, so it's just like it's looking at all of the derefs of R15 and saying how many do I have? That's all it is. So if it's reusing slots, then um, this should be correct. The interesting thing here is that the stack vars, we could use the same thing as this because it doesn't matter. It's just as long as they are unique. And rather than doing list max, we could do set from list set size. What are you gonna do? Okay. I think that this is fine, right? Uh, so let's run the tests again and like see what's wrong with this one that we just updated. Okay, and this one we might need to coming out with different orders. Line 85. We got two. Okay, so this is interesting. Um, line 96. For some reason, I thought RBX would never be used, but let's fix that particular assertion and then see what else fails, because I think that the rest of this is going to fail too. The generate allocations test. Okay. So yeah, we've got a thing here where um, we're pushing the callee save registers now. So I think that I need to, and then we get rid of the alignment call. Because it's now aligned. And this really just comes down to what was assigned RBX. I don't know. And then the conclusion. So now we're going to get down here, and the conclusion is going to be incorrect because what we've done is we don't need the alignment of RSP, but we do need to pop RBP off. Or RBX, excuse me. Yep. Okay, so that one's fixed. Let's go up and look at this one. Okay. So what's different here? Push RBP, move RSP into RBP, then align 24. I think that that's the same. So looking at main, push RBP, RSP, yeah, align 24. Okay, and then we are... Sorry, let me look back up here. Okay, so this is incorrect. Patch instructions should have fixed that, but I think that what we were doing here is... Yeah, that's incorrect code. You can't add two derefs together. Like one of them has to be a register. Whatever. Generate prelude and conclusion should not do anything with that. So what I want to look at is the sequence of instructions here. So this is this is our expected. So, but here, starting here is where we have our actual. So push RVP, move RSP into RVP, subtract 24 from RSP. Okay. Move 20 into RVP minus 8, move 22 into RVP minus 16, move RVP minus 8 into REX, move REX into RVP minus 24, add negative 16, okay, to 24, then move, okay, so then jump to conclusion. And I bet it's the conclusion that's different. Okay, and that's true, right? Okay, so what we want to look at is why did it not generate conclusion? Oh, you know what? It was because it was looking for main conclusion. And we excluded generating the conclusion if it's a tail call. But this is not a tail call. And this should be main conclusion. Right? Okay. Okay, so that was the big problem. Let's run this test again and see. It passes. Okay. So yeah, there's invalid code in here, but at least the generation is corrected. Okay. We are almost at time. I feel pretty good about what we've done today. Let's make a commit. All right, and I'm gonna close everything, close all. So I want to look at the diff. Okay, so we enabled that pass in our UI. And here, this big thing is fixing those conflicts. So the tuple type conflicts makes sure that every vector conflicts with the registers. Okay. That's just formatting. Here we fixed the bug. So this snapshot fixes the bug with the offsets. And same there on that snapshot. And then we adjust that assumption because we have changed what the conflicts are. We restored those tests. The only other bit here is I think that before we call this done, I want to not there in the test, please. I want to make a test which is our we'll call it generate functions test. And we're going to put our typical example that we've been using everywhere. Not that one, but this one. And we'll do snapshot. So we're going to do generate prelude and conclusion. P blocks P print format. What did we do before? Okay, this is where we had to deal with the definitions. So now they're just blocks. snap, and title is going to be generate functions test blocks. Okay. And let's Gleam test so we get a fresh snapshot. And this is the thing we've been looking at so far. Birdie. And I think that we have looked at this enough. We walked through it. I feel confident about it. So let's go ahead and accept it. Let's go back to our thing. So our test, what have we not staged? Here, we're adding that. Yeah, we did not stage that yet. Okay. All right, so finish chapter 7. We've fixed the root, and I need to make this big and bump up the text size because I can't read it. So fix the root stack dereferencing bug by making sure all tuple typed variables conflict with all registers, right? Okay, and then we re-enabled the generate functions, or generate prelude and conclusion test, and added a snapshot test to it. Anything else that we need to say that this did? I don't think so. All right. And I'm going to push that just real quick. I'm going to make sure formatting. Yep. All right. Okay. For some reason, it just doesn't keep my formatting consistent. I've been noticing that at work lately too. Okay. So I promised we would talk about what to do next. And we have options. So what we're going to do, let's look at the table of contents of this. So there are a bunch more chapters in here. We could talk about lexically scoped functions, which are basically lambdas, functions as values that are not global in the global namespace, right? My guess is here this is a combination of extracting their closures, generating global function names that can be jumped to, and desugaring their call sites into apply the closure, that sort of thing. Dynamic typing could be really interesting. And gradual typing, all this stuff is interesting. The generics would be really kind of cool to define types that are generic over various things. I don't know. We can continue, but I might also want to take a break. And I think I mentioned last time one of the things that I might want to break and do is revisit an old project of mine that's in Erlang, possibly reformulate it in Gleam. I don't want to break backwards compatibility in some ways, but there's also enough flaws in the original design that backwards compatibility may not be useful. Um, if we do that in Gleam, some things that were becoming hard in Erlang, hard to enforce, will become easier. And what I hope is that it would be better overall. And one possibility could be that, well, we just, say it's Gleam, and when it's published to hex, it's Erlang. It writes out the Erlang source. Or if it doesn't, then we could like make a release package that is the generated Erlang source, and make sure that um, there are limits to what sorts of Gleam libraries we use. I don't know if that's useful, like, because on the one hand, it's a tool. Um, I'm sorry I'm being dicey about this. It's Neotoma. And I should explain what Neotoma is so that you can, give me feedback. Um, Neotoma is a parser generator. So basically, its role is you give it a grammar and some transformations on matching nodes of that grammar, and it generates an Erlang module for you that you can use to parse languages that fit that grammar, parse inputs. I enjoy using that format because it doesn't have some of the limitations uh, of context-free grammars. Now, I really do enjoy um, the nibble. I think that's what it's called in Gleam. Um, and that's what we used in Essentials of Compilation for our parser. But it has some restrictions in that backtracking is really expensive. Um, Whereas backtracking in Neotoma, which uses parsing expression grammars and it is supposed to be a packrat parser but has some flaws to it, um, backtracking is cheap. In fact, it's expected. And it makes backtracking cheaper by memoizing intermediate results. So if you have, it doesn't do full extraction into tokens, and then you use like a stack machine to build up sub expressions from those tokens. Instead, it's top down. It says the entire input should be of this expression, or this expression is not the right word. It should be of it should match this rule, and then it's top down, so it uses recursive descent to try to match those. But at each point when it matches a non-terminal, that non-terminal can get memoized. So if you go and you try one branch and some of the non-terminals or terminals match, they'll get memoized, so that if you have a place where you try to use that that non-terminal at the same location in the input, it doesn't need to parse that again. It's already determined that that non-terminal matches at that point in the input. So again, backtracking is less expensive. The anyway, so that's the gist of what that project is. It takes a grammar, it generates an Erlang module for you that you can call parse this string or parse this file, and then whatever your transformations do on matching non-terminals, it will return you that data structure. So that's what Neotoma is. Um, the original version has some big flaws. The flaws are primarily that it you can only parse one at a time. What I mean by that is, for various reasons, it and those reasons mostly being my naivete as an Erlang programmer when I did it originally, is it creates an ets table, and um, that ets table stores the memorizations. So a mapping of non-terminal and position with the input to the resulting um, like memoized parse. Uh, that said, um, creating and tearing down those ets tables is expensive. They were named tables so that you didn't have to keep track of um, you didn't have to keep track of like the TID, the unique table ID. And then there are just a bunch of other things. So it also, a big flaw of it is it uses monadic parser combinators. So rather than completely generating code, it will basically um, use higher order functions to generate the parser. So it was like wrap functions around functions around functions, and then the little bits where you wanted to transform something, those would be just direct injected into an anonymous function. Um, and while it was pretty easy to understand the format. Like there was a real direct correspondence between what um, your input grammar said and what the generated code said. Um, but it was supremely inefficient. It meant that some of the optimizations that are in the literature for packrat parsers and parsing expression grammars could not be applied. Um, it also meant that rather than being able to do stuff like tail calls, you were always creating a stack frame. Um, and that this was not built with any of the typical compiler techniques. You didn't get continuation passing in places where it would be useful. You got instead just wrap, and it was more like generate a templated string than generating code. So that all said, um, it is to do it right is a big project. And I think that it would be multiple months, similarly to what we've done here with Essentials of Compilation. Um, it needs some serious thought about what is the structure, especially what is the structure of the passes. Uh, the benefit of doing the book for Essentials of Compilation is that's already been thought about really heavily by the authors, and it's just handed to you. Like, here's the set of passes you need to do, and here's what they do, and here's like very specific design decisions about preparing yourself to be able to transform something that's very abstract as this like Lisp like language into something very concrete like the x86 assembly. Now, we wouldn't be going as deep, but we would need to go from what are the Erlang semantics, um, and build our way up to what is the input grammar. through a series of phases, a series of intermediate representations that uh, operate on the individual like optimizations and code generation steps that we need. Now, luckily, we would kind of be going from something that sort of looks like a functional language to something that is a functional language. Um, so that part, that's sort of like, well, we can fill in the blanks and turn it into actual functions. Um, but there are some cases where some interesting things like some kinds of non-terminals don't need to be memoized. Like that's a particular optimization I was thinking of. And so what they'll do is they'll look at they'll build a cost function over every non-terminal and go, what's the cost of this? Um, and if the cost is below a particular threshold, you can say, well, this thing doesn't need to be memoized because it's going to be cheaper to just call it every time you need it than to try to memoize it and fetch the memoization and all the copying that might be involved there. So that's a particular thing. They call that virtual inlining. There's some bits where there needs to be a fixed point optimization over the grammar, removing particular things, um, flattening constructs that, like for example, might be generated by something earlier in the process. Like if you have an alternating, so like this non-terminal could be this or this or this, but you have only one option there, then you can remove that choice. Like that's a very simple optimization and flatten it to a sequence. Um, or if you have a sequence with only one thing in it, you can remove the sequence and it can be just the thing. Excuse me. Uh, so there's all sorts of things like that um, that I think would be really interesting to attempt. Um, the first bit is the hard part, the planning. So I'm considering that. There's also I would love to go back to game dev for a bit. So we could do some more tiramisu. There's a genre of game that I've been seeing a lot more of lately that would be interesting to see how that sort of thing gets put together. Um, so anyway, drop me your thoughts in the chat or on Discord if you're on the Gleam Discord, and let's talk about what to do next. Thanks for hanging out and for staying a little bit extra long, and thank you for the interaction in the chat. I hope you all have a wonderful day, and we